Thanks. Yeah, so today I'm going to talk about some work that was done fairly recently, but I was still in Google Research before I joined Google DeepMind. I know for some people it's the same. They're not exactly, but yes, yeah, it's a bit of a mess. So this work is anchored in medical AI, but it actually doesn't need to be. And it was led by Alex Brown, who was an AI resident at Google at the time. So we're going to talk about detecting shortcut learning for fair medical AI. So what do we mean by fairness, and in this case, medical AI? So due to various correlations in the data, models can learn sensitive characteristics, like age, gender, race, whatever proxy we have for them at least, even when they're not trained to do that. So, it's not really a surprise that we can predict the age from maybe like somebody's skin or a picture of it. But if you predict a disease, you actually see that the model is also able to then predict the age of the patient. And this can lead to biased predictions, although it's not a sufficient condition for that. So even when you learn the sensitive characteristics, your model might actually not necessarily use it for its predictions. So the definition of unfairness we're going to use in this talk is disparities in model output across demographic groups. It's a fairly accepted definition, and it's quite broad. What we're going to specifically look at today is we're going to focus on model performance. There are different reasons for that, but because this is a medical imaging task, this is actually what not only based on discussions with clinicians, but also in terms of what we expect the data generating process to be. Then this is a metric that makes most sense in terms of giving a mathematical definition for fairness. So we're going to look at different model performance across groups. So that's the fairness side. And we can see that we have an example here where we have a model that's trained to predict effusion, so it's liquid on the lungs, for different patients. And we have that for a patient who's age 30, the model is actually not predicting the correct category. And for a patient that's age 76, the model is actually predicting the correct category. Now, especially in medical AI, but in a lot of real world cases, it is really difficult to say that if you have unfairness, it means that your model is amplifying bias from your data set, or that it simply shouldn't be there, or that you can find a model that is completely fair and does not affect performance. The data generating process and what we're going to call shortcut learning for the purpose of this talk. So this is actually a definition from Garrison, where when the model relies on a signal that can vary across environments. And if you look at here, the small graph, it's not really a causal graph, so like don't worry too much about it. It's just an illustration. So you have different labels, which are the conditions that you want to predict. You have an image, which is in this case chest X-rays, and you also have your attribute. And we believe that from your image, you actually have enough signal. It's a sufficient statistic to predict your condition. But in some cases, actually, also including signal from the attribute might help So what you want to know is whether the model, like whether you are in the case where it actually is a sufficient statistic, and you should only really be using the signal from your image and not the signal that is related to your attribute, or whether there's actually a causal link or like an influence of your attribute on both your image and your condition, which might be based on biology. For example, like we know that age especially like affects people's health. And so we really want to try and disentangle cases where the model is really amplifying some of that signal, and there might be fair alternatives, compared to the case where, well, actually, this is the most fair you're going to get with this data set and model, even if you remove the signal from the attribute. So this was previously operationalized in different ways. You can look at performance on data that's out of distribution, and you can look at worst group performance as well. We're going to look a bit actually more on the fairness metrics, but they're actually quite equivalent because shortcut learning was mostly defined for robustness, and so that's why the robustness metrics have been privileged. But it doesn't mean that fairness metrics are suited as well. There's actually a pretty clear correspondence between worst group performance and metrics like equalized odds. Now, what we've seen as well is that the mitigation to unfairness has also been it's almost been binary. It's almost been, oh, well, we don't want any reliance, so we're going to cut this link, we're going to remove all of the signal, and we are potentially going to hurt some of the model's predictions for specific groups or for the whole population. But this is what we want to do because we don't know what else to do. And in other cases, actually, it comes a lot in discussions with practitioners where model performance is privileged, and especially when you start thinking about medical AI and how you have to go through various like compliance requirements and things like that. So model performance is really one of the key indicators there. And then at this time, then potentially nothing is done. So it's a bit like either you use the regularizer to completely remove, or maybe you just then leave it because you don't really know whether the source of the unfairness is due to the model amplifying or whether it's due to a potential causal link. So can we actually separate the two? So we're going to look at some of the hypotheses that we have here in terms that the shortcut learning actually will appear if by increasing the sensitive attribute encoding in the model, we're also going to affect fairness or unfairness metrics. So you can view this as a bit of a dial where if you push it towards like strong negative values, then you're going to push your model to not encode the sensitive attribute. So this is adversarial training. You put it to 0. This is your original model without any regularization. But you can also increase your encoding where you're actually encouraging the model to encode the sensitive attribute. And you look at the effect of this dial on your fairness metrics and also on your performance metrics. So how do you actually put that in practice? It's quite simple. So you have like your network where the last layer gives you the outputs. Then during training, you have your gradients. So what you do is you add, you need at least 2 layers here with some nonlinearities. But you also predict, it's a bit of a multi-objective type of learning where you also predict the sensitive attribute. And you have this lambda times the gradients. And this lambda is really this dial here. So you put it negative, you have adversarial training. You put it positive, you have more of a multi-objective. And so this is what we're calling the sensitive attribute head. And during testing, what you do is, so you remove this part and you freeze all of your other weights. This is kind of your feature representation. And you measure performance, fairness, and then this metric, which is also the encoding of the sensitive characteristics, where you add, in this case, a linear layer to see how much of the sensitive attribute is encoded into your network. So there's nothing really new about it, really. But what we look at is then the correlation between how much the model encodes, and here we're looking specifically at age as a sensitive attribute, compared to how fair or unfair it actually is. If your model fairness does not vary with the differences in encoding, it means that whatever level of unfairness you have does not seem to be driven by the encoding of age, while if you have a strong correlation or anti-correlation, depending on your sensitive attribute, you actually see that your model, by relying on the sensitive attribute, does create more unfairness. So what does that look like in practice? So we did a couple experiments, and here I'm going to show mostly the age in chest X-rays. So we have this data set from the NIH, and we binarize things. So we have a population that does not have effusion as a diagnosis, and population in green that does have effusion. And you see a slight difference in the mean age between those two distributions. It's fairly small. It's actually not that bad. So we train multiple models. For each model, we train multiple seeds, and also we vary this lambda, so the strengths of our gradient scaling. And we have different bounds here. They're not theoretical bounds, they're experimental, where if you just take your network and you train it to predict age, this is the lowest bound you can obtain. So this is the minimum error you're going to make. While if you randomly predict age for a patient, then this is kind of what you get in terms of your error. So when you perform this gradient scaling, you really want to cover that whole space in between the two bounds. And the orange ones are the 0, so basically no gradient backpropagation. So we can see that we're able to cover the whole space quite nicely. And then we can plot the fairness, the performance with regards to the age encoding. Again, the orange dots are the ones without any regularization, and we can see that there are models that include more age and that are as performant, and they're maybe a bit more unfair. And then you have a couple models that are maybe less performant. They're also less unfair. And then you have models that become quite trivial as well, where you're getting in here. So as I mentioned, this was quite a small difference between our two populations. So we've engineered some of the data set basically by subsampling to create a larger difference here of around 10 years in the mean age across the two populations. And here we actually have matching distributions, again by subsampling. We call this like the balance. And what we see is that in both cases, we're again still able to cover the full range, but we see quite different patterns, right? So you have here the models are much more unfair, and then you have clouds of models that actually perform quite well, probably close to what we had in the previous slide, and that are more fair. While if you train from balanced data, you actually see that you have models that perform really well. Most of them perform really well and do not have a lot of unfairness. And in this case, actually enforcing forgetting of the signal, because there's actually not much signal there, you might even hurt performance. So it really gives you kind of this it's not really a frontier, but it's more like of an experimental range of the fairness performance trade-off you might obtain, which in this case, actually, you don't really need to trade off. So in terms of observations, we see that this method of varying the gradients and looking at the correlation between the fairness and the encoding actually correctly detects shortcut learning when a spurious correlation is engineered. And we also have simulations in the paper that shows that for both the positive and negative cases. So for the original data set, we have a really slight correlation. For the biased data set, we have a really strong correlation. And for the balanced data, we do not have a correlation. Now, if we just like take all of these dots and we plot lines instead, just to make it a bit clearer, then we can see that the encoding of a sensitive attribute is actually not predictive of a model's fairness characteristics. So this is coming back to the fact that even if your model encodes, it doesn't mean that it's going to use it. But it's just more general that encoding doesn't really tell you what your model is going to do or not. Unless you have really like zero encoding, then you actually really don't know what your model's fairness characteristics are going to be. And we can see here for the biased, we can actually, for the same level of encoding, we can have very different fairness properties, right? What we also have as a bit of a secondary observation is that subsampling is quite effective. And in this case, because adversarial learning can be quite difficult to pinpoint in terms of hyperparameters, subsampling here actually outperforms it. And we see that we are able to have models that have really high performance on a smaller sample of the data set if the balancing is done correctly. This is also observed in other cases not related to medical imaging in this paper by Idrissi et al. Now, we still have the case where shortcutting is not potentially the main source of unfairness. So the nice thing is that, as I said, we have a range of fairness performance trade-offs. So here we are actually looking at a dermatology data set where we're classifying acne versus no acne. And the population for acne is really skewed towards younger patients compared to patients with no acne. And we can see that the models are actually not that fair, but there's no clear pattern. And there's actually no clear correlation. It's just the model is unfair. And it's not really clear what we can do about it at this point. But still, like there's this model or that model, they have very similar performances to the ones in orange, but they're actually more fair. And so we could try and find more models pushing back in that direction while keeping the performance. So as a conclusion, so in terms of the advantages and drawbacks of this technique, in terms of advantages, it actually does not depend on a specific fairness or utility metric. You can use anything you want and consider potentially health equity or more downstream impact metrics if you wanted to. As a byproduct, it does provide alternative models where you can maybe pick more of your fairness performance trade-off. And we have validated some of our findings with simulated data. Now, in terms of drawbacks, it requires training multiple models, which can be expensive. Maybe, we trained 125 models. I'm not sure you actually need to go to that length, but it still can be quite expensive. And performing the hyperparameter selection can be quite difficult. We have identified starting points that have actually been generalizable across models and data sets, but there might still, we've converged and we have satisfactory results, but there might always be hyperparameters that might be even better. So I would say that hyperparameter tuning in this case remains a bit of a challenge. And so what we've seen is that potentially also in adversarial training, it's not matching distributions. It's not really just matching f of x in terms of your sensitive attribute. Once you have the predictions, it actually sends the gradients all the way back. And so it could potentially remove the signal. And when it removes the signal, it also removes everything that's correlated with it, which can then, if you have very correlated signals, then really affect performance. And as we've seen, encoding does not imply unfairness. And although unfairness typically implies encoding, so we've seen that, when we don't vary, it's because the model is actually fair. But when you have unfairness, you also have encoding. And when you have fairness, it does not imply that you do not have encoding. So this is another thing, if you want to freeze your weights and give them to somebody else, it doesn't mean that they're going to have a representation that's there. And I think this is an important distinction. So that closes it for me. I want to thank my collaborators and all of the people at Google DeepMind who have been involved. They're not all listed here. And the organizers of the webinar for having me, and all of you for your attention. And I'm looking forward to questions. Thank you.